and welcome to the Chemistry Academy. In this video we're going to go over the 2025 SQA Higher Chemistry paper 2. If you are looking for help with the multiple choice paper 1, then you'll find that in a separate video. In this video we'll probably actually only go over the first half of section 2, so again if you're looking for help with the questions in the latter half of section 2, then you can find that in again a separate video, and they'll all be on my Higher Chemistry playlist. So if we get started with the first question, they're easing you in a little bit here by asking you to write the equation for the first ionization energy of sodium. Now this is a question you should never get wrong because the answer is essentially in the data booklet. So if you go to the page that has all of the electronegativity values and ionization energies on it, you will see at the top that it's got the generic ionization energy equations. So we're looking for the first ionization of sodium. So we would use the one that starts with the neutral E atom, and all you have to do here is copy the equation exactly as you see it, replacing the E with the symbol of the element you've been asked to give the equation for. So because that is sodium, the symbol will be Na. So we have Na as a gas going to Na positive as a gas plus 1 mole of electrons. Make sure you remember the G state symbol. If you don't have that, then you will not get the mark. So then question 2 is using the ionization energies from the table, calculate the energy required in kilojoules per mole for the following reaction. So in these questions, what you have to do first of all is identify what ionizations are actually taking place. So we can see we're going from a neutral carbon atom to a neutral calcium atom to a calcium 2 positive ion, and you can see how many ionizations have taken place because there's 2 moles of electrons, so that tells us 2 ionizations have happened. So if we're going from the neutral atom to a 2 positive ion, that means we've undergone the first and the second ionizations. So we need to add up the first and second ionization energies for calcium. So if we add those together, get my calculator, 1145 plus 590, that should give us 1735 kilojoules per mole. You don't need to write the units, but if you do, they must be correct. Ionization is always an endothermic process, so the energy is always going to be put in, so you can put the positive here, but you actually didn't need it in this case. So then part 3, explain fully why the second ionization energy of sodium is much higher than the second ionization energy of magnesium. So in this occasion we are comparing 2 different types of element, types of atom. So the best thing to do here is to look at the periodic table and see where they are in relation to each other. So we're looking to compare sodium and magnesium. So if we look, sodium is here, magnesium is here, so they're across a period from each other. This means that we're looking for what the explanation of a trend across a period is. So we know that as we go across a period, there's always an increasing nuclear charge. So if magnesium has a higher nuclear charge than sodium, then of course its second ionization energy is going to end up being higher because So in question 3, we're asked to explain fully why the second ionization energy of sodium is much higher than the second ionization energy of magnesium. So if we have a look at where these elements are in relation to each other in the periodic table, we can see that sodium has got the electron arrangement 281 and magnesium is 282. So the main difference between these two when they end up with their second ionization energies happening is that for sodium, when you start to do the second ionization, you're then removing an electron from a shell that's closer to the nucleus, and then also therefore that the electron that's trying to be removed is going to be more attracted to the nucleus, so it's going to be more tightly held. which means you're going to need more energy to remove it. Whereas for magnesium, the second electron is getting removed from a shell that's further from the nucleus, and then therefore it's going to be more shielded, so it's going to be less attracted to the nucleus, therefore you need less energy to remove it. So the 2 marks here come from the first marks really for you either stating that in the sodium that the second electron is coming from a full and stable electron shell or a shell that's closer to the nucleus. The second mark is then you referencing how strongly that electron is then therefore attracted to the nucleus. So the second electron in sodium is more strongly attracted to the nucleus, or you could say that the second electron in the sodium is less shielded. So there's less layers of inner electrons shielding the nuclear charge, which means that the electron experience a stronger nuclear attraction. So I'll just put down the second electron is from a full and stable shell in sodium. So, and is less shielded from the nuclear charge. Okay. Sometimes if you struggle with these, it's a good idea to write down the electron arrangements for what's happening. So if you're doing the second ionization energy of sodium, then you're going to be going from 2,8 to 2,7, because sodium positive has got the electron arrangement 2,8, and then if you're going to Na2 plus, that would be 2,7. Whereas with the magnesium, so if we're starting with Mg positive, that's 2,8,1, going to the Mg2 positive, which would be the 2,8. So that should help you see where the electrons are coming from and then how shielded they are and things. So the more levels of electrons, the more shielded that outer electrons will be. Therefore, it makes them a bit easier to remove because they'll be experiencing less of that nuclear charge. It's very important with the ionization questions as well that you reference what ionization you're talking about. So here I'd mentioned this, that it was the second electron that was being removed. I actually forgot to put in the removed, so I probably should say is removed from, and then it shows that you know that the electrons are being removed. Or you could say the second ionization energy requires the removal of an electron from a full stable electron shell and an electron that is less shielded. So just make sure you're very clear with your wording in these questions. So then part 4, the magnesium 2 positive ion and the sodium ion have the same number of occupied energy levels. Explain why the Mg2 plus ion is smaller than the Na plus ion. So again, when you're comparing sizes of things, it's a good idea to write down the electron arrangements of these things. So for sodium, the sodium ion, if we look at what its electron arrangement will be, it'll be 2,8. The magnesium ion will also be 2,8. So they both have the same number of occupied shells, which means that the number of electron shells is not what's causing the difference in size, so it must be something else. The only other thing that can cause then the difference in size is the nuclear charge. So if we look at comparing the sodium and the magnesium, magnesium has more protons, it's got 12 protons in its nucleus, so that means it's got a greater nuclear charge. So that means its 8 outer electrons are going to be pulled in closer to the nucleus rather than in the sodium atom, sodium ion rather. One thing to make sure of for these questions is you don't mention anything to do with covalent radius or things, because this is talking about ions. So you can talk about ionic radius, but if you were to mention covalent radius, that would take the mark away from you, because again, we're talking about ions, not atoms here, and covalent radius is to do with the size of the atom. So in terms of answering this question, a simple that the Mg2 plus ion has a greater nuclear charge would be completely fine. Again, with these questions, there are slight different ways you can word them, but so you could say that it has more protons, but yeah, either mentioning number of protons or nuclear charge is probably the safest option with these sorts of questions, and I would probably recommend nuclear charge over numbers of protons sometimes. So then B, potassium formed ionic bonds, state what's meant by the term ionic bond. A lot of you, I did see some people on TikTok commenting on this question, because this is actually probably more a Nat 5 thing. So this is you having to go back into your memory really of what you learned at Nat 5 for the definition of ionic bond. But it is, if you remember, an electrostatic attraction between oppositely charged ions. The electrostatic attraction bit is very important. If you were to just have said that it was where positive and negative ions are attracted to each other, or bond between oppositely charged ions, unfortunately, I don't think that would be sufficient. So the electrostatic attraction is a key component to the definition of ionic bond. And if you were to look up the course support notes for the National 5 course, or even a higher one, it should be in there as well. So if you are making up flashcards for definitions when you're studying, I would advise going and looking at the course support notes that you can find on the SQA website and using the phrasing in the course support notes for your flashcard definitions, because again, I can't emphasise how important the wording is in these things. So now we've got part 2. So I did see a lot of questions or comments about this one on TikTok as well, the bananas question. So this is one of those numeracy questions. So the way I like to approach these is to sort of lay out the numerical relationships that you're given. So it tells you that the adult takes 8 tablets per day for 7 days. So in one day they have 8 tablets. So then in 7 days we can work out how many tablets that would be, and that would just be 8 times 7. So that's 56 tablets that they'll take in the 7 days. And then it tells you that each tablet contains 0.0012 moles of potassium. And then it gives you the GFM. And then it tells you that one banana contains 450 milligrams of potassium. So, and then we're asked to calculate the number of whole bananas. So because we need a number of bananas, I always like to put the question mark underneath the thing I'm trying to work out. So we're trying to work out bananas, so the question mark's going to go under there. So that tells us that we probably need to start over here, because if we're going to finish with this relationship, we're probably going to need to use this one to start off with. So we're trying to work out a mass of potassium that they need over the days. So we know that one tablet will give them this many moles of potassium, so we can work out how many moles they would get in 56 tablets, because that's how much they're going to be taking. So we would do the 0.012 times by 56, and that gives us 0.0672 moles, sorry. But now we need to convert that into a mass. So we know the GFM of potassium is 39.1. So to convert that into a mass, we would just times the moles by the GFM. Remember, M times GFM. So M equals N times GFM. So that would be 0.0672 times by 39.1. So do that, we get 2.62 752. It's good not to round your numbers in the middle of calculations if you can. And that is in grams, but we need it in milligrams because our mass of potassium in the banana is in milligrams. So to convert from grams to milligrams, we need to times by 1,000. If we times that by 1,000, we end up with 2627.52 milligrams. So now we can put that underneath the milligrams of potassium over on this relationship, and that means we can then scale down and scale up. So we need to scale to 1 milligram, so that'd be the one banana over 450, and then we times up to the number that we need. Oops, so that would be times by 2627.52. So if we do that in our calculator, we end up with 5.838, but we need, or 839, but we need whole bananas, as it says here. So that means that we would have to round it up to 6 bananas. Oops. Okay, so it is a bit of a longer, there's probably more steps in that numeracy question than there would be in a normal, usual one, but yes, hopefully that made sense to you, especially if it was on exam day and you're not just revising. So question 2, we've got information about 4 elements from the 3rd period of the periodic table, and we're asked to complete the table to show the bonding and structure for each element. So sodium is a metal element, which means it'll have metallic bonding. So again, this is a bit of your sort of National 5 knowledge coming in here. Phosphorus is a non-metal element, and so that will have covalent bonding. Silicon, you should remember that it's a covalent network. And then chlorine is one of the diatomic elements, so it would also be covalent molecular, much like phosphorus. But remember, phosphorus is P4, it's not diatomic. So then the covalent radius is half the distance between the nuclei of 2 covalently bonded atoms of an element. State the trend in covalent radius going from sodium to chlorine. So going across a period, the covalent radius will decrease. This you can actually find in the data booklet. If you look up the covalent radius periodic table page, you can see it decreases going across the period. They've not actually asked me to explain why in this one, so you don't need to. But normally if we were explaining trends across the period, it's always because of an increasing nuclear charge. So all you really have to say for this one is that it decreases, and that should be sufficient. If you did say anything else extra, as long as it was correct, that would be fine. So then, suggest why no covalent radius is listed in the data booklet for argon. So remember, covalent radius is the measure of, well, as they've told you here, it's half the distance between the nuclei of 2 covalently bonded atoms. We know that the noble gases don't form any bonds, therefore they would have no measurable covalent radii. It's not enough here though to say that they're monoatomic or that they don't react or they're inert, because the key here is the reference to the fact that they don't actually form any measurable bonds. So you need to make, in these sorts of questions, if you're asked about why any of the noble gases don't have a covalent radius, please make sure you mention the fact that they don't form any bonds. Okay. Again, if you were to say extra stuff like they don't react and therefore don't form bonds, that's perfectly fine, because they don't react, that's correct. But the key bit here is that they do not form bonds. So then part C, explain fully why the boiling points of noble gases increase going down group 0. In your answer you should name the van der Waals forces involved. So with the noble gases, they have London dispersion forces. Even though they don't have any covalent bonds between their atoms or anything, they'll still have London dispersion forces because they still have electrons that can become unevenly distributed. The strength of the London dispersion forces increase going down the group because you have increasing numbers of electrons as you go down, and the more electrons you have, the stronger your London dispersion forces will be. So for this one, the 3 marks really come from 1, identifying that there's London dispersion forces present, 2, for stating that the strength of the London dispersion forces increase going down the group, and the 3rd one is really from then saying that the strength of those London dispersion forces increases down the group because of an increasing number of electrons. So that's where your 3 marks are coming from there. So then, open-ended question, the first one is pure covalent bonding and ionic bonding can be considered as opposite ends of a bonding continuum. Comment on how the position of a compound on the bonding continuum can be explained on how this can be used to predict its bonding and properties. So the bonding continuum, which I'm sure you probably know, is from pure covalent all the way to ionic. So sketching out a bonding continuum is probably a good start. You then want to talk about then electronegativity, because, and then in the middle we and with it's not ionic or pure covalent, it would then be classed as polar. I can't spell very well. But things you would then want to talk about is electronegativity. Again, giving definitions is always good in these. So give the definition of electronegativity. talk about the differences in electronegativity. So if it's ionic in character, there will be a large difference in electronegativity. If it's pure covalent, the electronegativity values must be exactly the same, and therefore the electrons, bonding electrons, are equally shared. Then you want to ideally then go on to talk about then how this helps you work out then bonding and properties. So then you'd want to go on to talk about solubility, melting and boiling point. For ionic compounds, you would really be more sort of Natch 5e level, I guess, that ionic substances can dissolve in water because they have opposite charges or partial charges, which polar water molecules also have. And then just generally stating that ionic substances tend to have high melting and boiling points because ionic bonding is relatively strong. Then you would want to talk a lot about polar covalent molecules and non-polar covalent molecules because that's what you can learn about mostly this year. So talking about polar molecules, giving examples of polar molecules, so you could draw like an ammonia molecule, for example, label the dipoles on it, talk about how then it's got a permanent dipole. It can then form hydrogen bonding because the hydrogen is bonded to nitrogen, which creates a strong permanent dipole. And then you can talk about then that allowing it to be soluble in polar water. Giving examples of other polar molecules, just like even hydrogen chloride, how that has only then permanent dipole to permanent dipole interactions. Then talking about the relative strength of those things, like that hydrogen bonding is stronger than permanent dipole to permanent dipole interactions. So you would expect ammonia to have a higher boiling point than the hydrogen chloride. And then the non-polar molecules, it's really just talking about London dispersion forces, the fact that they're non-polar, so then they would only dissolve in non-polar solvents such as hexane or oil and things like that. But trying to make sure that you did go on to talk about the properties and didn't just focus on the bonding continuum and stuff being like polar versus non-polar. Okay, so there's quite a lot to talk about in there. It's kind of just really a bit of a word dump of all the bonding properties you've done, and like I said, ideally focusing on the van der Waals forces, because that's the main stuff that you learned at higher. Okay, so then balancing the equation. So my preferred way to balance equations is always to go from left to right through the elements. So if we start with the carbons, there's 3 carbons there, which means we would, over here, which means we would need 3 moles of carbon dioxide. Then we've got 8 hydrogens altogether on the left, because there's 7 and 1, so that means we need a 4 in front of here. And then now if we look at the oxygens, so there's 1, 2, 3 on this side at the moment. On this side there's 3 times 2, which is 6, plus 4, which makes it 10. So what you have to remember here is that there's 1 oxygen here already, so we actually only need 9 oxygens from the O2, which means that we need 4.5 moles of the oxygen. Now this one is a balancing equation is slightly different to most, because most of the time if you have half moles you can multiply through by any multiple to get rid of the half, and that's usually fine. So you could have multiplied through by 2 here and had 2 moles of the propan-1-ol, then it would be 9 moles of oxygen, 6 moles of carbon dioxide, 8 moles of water. However, in this one it wants the equation for the enthalpy of combustion of propan-1-ol, and enthalpy of combustion by definition is the energy released when 1 mole of a substance burns completely in oxygen. So you can't have more than 1 mole of the ethanol here. So this is a little bit tricky one for the balancing equation, but yes, just remember enthalpy of combustion is always for 1 mole of the substance. So in this case you had to use the half moles of oxygen, and the place most people maybe potentially went wrong was forgetting there was already oxygen in the alcohol, so you had to take 1 off the number that you needed. So then an experiment was carried out to determine the enthalpy of combustion of propan-1-ol. The results are shown in the table. calculate the enthalpy of combustion of propan-1-ol in kilojoules per mole for this experiment. So we've got some data from an experiment, so we're going to use EH equals Cm delta T, because if you're ever asked about energy, enthalpy of combustion, and given like temperature changes and things, you will have to start off with EH equals Cm delta T. So C is 4.18, as we should hopefully all know from last year. The mass is the mass of water, which is, at the top, you can't see it here. And that, if it's in centimetres cubed, that's grams, so we need to divide it by 1,000 to convert it into kilograms, so that'd be 0.15 kilograms. So we put that in. And then the change in temperature, we would need to take these away from each other. So 35.1 take away 21.2, so that'd be 13.9. So you just type that all in, 4.18 times 0.15 times 13.9. And that gives us 8.7153 kilojoules. And again, I try to encourage no rounding until the end of the calculation if possible. It just makes them, if someone's marking your exam, it makes it a bit easier for them to make sure you've got the right answer. So that's how much energy we got from burning this much propan-1-ol. We want the enthalpy of combustion, which is how much we would get from burning 1 mole. So we need to set up a little direct proportion relationship. So 0.498 grams gave us 8.7153 kilojoules. But we want the amount 1 mole would give, and it gives us the GFM of propan-1-ol here, 60. So we need to find out how much we would get for 60 grams. So we can scale to 1 gram. So even though it's a decimal, you're still dividing, because it's like if you imagine that was 498 rather than just 0.48, you'd be dividing by 498. So you're still dividing by 0.498. So we'd have 8.7153 divided by 0.498, and then to scale up to the 60 grams that we're looking for, we would then times by 60. So if we put that in our calculator, 4.7153, you can actually keep these numbers in your calculator. I don't know why I keep clearing them out, I'm just making my life harder for myself. And then times by 60. And that gives you 1050.04, say, kilojoules. Now, one thing you need to always remember about enthalpy of combustion calculations is that they will always be negative, because combustion is always an exothermic process. So you need to put the negative sign at the front of your number. If you don't, you will lose a mark. It's hard to remember that one because your calculator doesn't churn it out as a negative, so just please try to remember anything to do with enthalpy needs a plus or a minus sign in front of it, and if it's enthalpy of combustion, it will always be negative. So then part 3 is naming the pieces of laboratory equipment that are essential for carrying out this experiment. So for the energy from fuels experiment, we need usually a copper can or some form of container can, but copper one's the best. You would need the spirit burner, you would need a thermometer, and you would need a tripod to put the copper can on. They are the essential things. You also need a balance as well to measure the weigh the burner before and after. You could also, rather than having the tripod, you could say a clamp stand. That would be suitable as well. The things that are not essential, although we do recommend, would be like the draft shield, a heat mat. So they're not essential pieces of equipment, so they wouldn't probably be awarded the marks in this case. So you are really looking for the, like they say, essential things here. So that would be the clamp stand, the copper can, the thermometer, and the spirit burner, and the balance. So that would be the main things. So then, suggested reason why the enthalpy of combustion determined experimentally is lower than the value given in the data booklet. So There's always a couple of reasons that are commonly known for why, when we do the experiment in the classroom, the results aren't as high, like the enthalpy of combustion doesn't come out as high as what it says in the data booklet. The two reasons that are easiest to remember would be that incomplete combustion has taken place in the lab, so then you've not burned the fuel completely, not released all the energy, or heat energy is lost to the surroundings. You can also mention about the fuel evaporating from the wick, but that's not my favourite one to remember, just personally. So I always like to remember the heat being lost to the surroundings and incomplete combustion taking place. You can have either of those. Then alcohols can undergo oxidation reactions. Oxidation reactions involve a change in the oxygen to hydrogen ratio. Determine the oxygen to hydrogen ratio for the alcohol ethane 1,2-diol. So it's probably a good idea to sketch this out. So ethane's 2 carbons, and if it's a 1,2-diol, it means it's going to have 2 hydroxyl groups, and then everything else will just be hydrogens. So then once you've got your picture, you can just count them up. So there's 1, 2, so we want the oxygen to hydrogen ratio, so there's 2 oxygens, and then there's 1, 2, 3, 4, 5, 6 hydrogens. You can simplify this 1 to 3, but as keeping it as 2 to 6 would be fine as well in this case. Okay. You could also put the ratio the other way around as long as you clearly showed which was which. So it's usually a good idea just to look at the question and see what way they want the ratio to be, so if you're going to end up forgetting to label it. So then a primary alcohol X with the formula C4H9OH can undergo oxidation to compound Y, suggest a suitable oxidizing agent for this reaction. So we're looking to oxidize an alcohol. So to oxidize alcohols, we generally want to use hot copper 2 oxide or acidified dichromate solution. Feeling solution and Tollens reagent are not strong enough oxidizing agents to oxidize alcohols, so we don't really tend to use them. So for these questions on oxidizing alcohols, you really do need to pick hot copper 2 oxide or acidified dichromate solution, ideally, for these. And then compound Y can be oxidized to give product Z, which turns universal indicator red. Draw a structural formula for product Z. So if it's turning universal indicator red, that means you produced a carboxylic acid. If you've fully oxidized this alcohol to form the carboxylic acid, you're going to end up having formed butanoic acid because you've started off with 4 carbons. So drawing the structural formula for that, you do your 4 carbons in a row, put on your carboxyl group, and then add in all your hydrogens. Just like so. So then part C, alcohol X has an isomer that is a secondary alcohol. Name the product that will be formed by oxidation of this isomer. So if you've got a secondary alcohol with 4 carbons, that would be like, say, butan-2-ol. And then, so if you're oxidizing a secondary alcohol, you're going to make a ketone. So if you've got a ketone with 4 carbons, then you would be making butanone. You don't need the number for where the carbonyl group is in the ketone because it can only be on carbon 2 if you've got 4 carbons. But if you call it butan-2-one, it's not the end of the world. But anything above 4 carbons for the ketones, you would need the number for where the carbonyl group's located. So then for C, the concentration of a solution of ethanoic acid can be determined using sodium hydroxide solution. A solution of ethanoic acid was prepared using a piece of glassware that allows the volume to be made up to exactly 250 centimetres cubed. Name this piece of glassware. So if you're preparing solutions, then you're usually using a volumetric flask or a standard flask to hold the solution. If you were measuring out volumes of the ethanoic acid to be made into solution, you'd probably use a pipette or potentially a burette, but for actually preparing the solution and holding up a volume to 250 centimetres cubed, that would be the volumetric flask or the standard flask. So then a titration was carried out to calculate the accurate concentration of ethanoic acid solution. The burette was rinsed with the deionized water and then filled with sodium hydroxide solution, suggesting improvement that can be made to this step in the titration procedure. So we really don't want to rinse our burettes through with water or our pipettes and then add the chemical straight in, because there could be residue of water left in the apparatus and that could dilute our solutions, which is not good if we're doing volumetric analysis, because we want our concentrations to be accurate. So what you should really do is rinse your burette through with whatever solution you're going to be putting in it. So in this case, it would be the sodium hydroxide solution. So they should have rinsed the burette with the sodium hydroxide solution instead of water, or at least if they rinsed it through with water, then rinsed it through with sodium hydroxide solution after. So then using the results to calculate the average volume used. So we only want to use concordant results. We never usually use the rough titration, even if it is concordant. And so then out of the remaining results, the only concordant ones are these two here. So you would do 20.5 plus 20.3 divided by 2, and that should give you 20.4 centimetres cubed. With this one here, I think you actually get 20.4 if you actually just added up all 4 and divided by 4. If you just written 20.4 as your answer, then that's probably fine. However, if you were to have shown working that showed that you'd used all 4 values, I'm not really sure that would fly. So yeah, just remember, always only use the concordant results when you're calculating your averages from titrations. So then in another experiment, 25 centimetre cubed samples of ethanoic acid were titrated with 0.105 moles of sodium hydroxide solution. So we're just doing a titration calculation here, and it's quite a straightforward one because there's only 1 mole of sodium hydroxide reacting with 1 mole of ethanoic acid. So when it comes to laying out calculations, I quite like to write the formulas, or at least the names of the chemicals if you don't know the formulas. If they're not giving you an equation like in this one, you can at least write names. You could write sodium hydroxide or just even sodium and then ethanoic. And we're calculating concentration. So we've got N, V and C for both because we're dealing with a titration, and they've told us it's a 1-to-1 ratio, so that goes in the middle. Then if we do our, like I like to say, a really crap chemistry treasure hunt and look for our numbers. So we've got volumes of ethanoic acid samples. Just remember to change your volumes into litres, so divide by 1,000. So for that it would be 0.025. And then, that's an L for litres. And then we've got a concentration of sodium hydroxide solution. So I'll put that next to C here. Just remember, anything with moles per litre after it is a concentration, not a number of moles. And then you've got the average volume of sodium hydroxide solution used was 19.8, so that's a volume of sodium hydroxide, and again we need to divide by 1,000, so 0.0198. And then it wants us to calculate the concentration of ethanoic acid, so I always like to put a question mark with where I'm ending up to remind me where I need to go, and that shows me that I'm probably going to be starting here. So N is equal to C times V, so put that in our calculator, 0.0198 times by 0.105. That gives you 2.079 times 10 to the minus 3. It's a 1-to-1 ratio, so then that just stays the same as the number of moles on the other side. And then C is equal to N over V. So we would just take that number of moles and divide it by 0.025. And that gives us 0.08316. That would be moles per litre because it's a concentration. Again, you don't need to write the units because they are given in the question, but if you do write them, they do need to be correct. So then, question 3, write the ionic formula for potassium ethanoate. So remember, when you're forming a salt with carboxylic acid, all that happens is the hydrogen comes off and the potassium or the metal takes its place. So we would end up with CH3COO and then K. But we need the ionic formula, so we need to put on the ion charges. Potassium is probably the element one we're most familiar with. It's in group 1, so it's going to always have a 1 positive charge as an ion. So we know that's going to be 1 positive, which means to balance that charge out, it means the ethanoate must be a 1 negative charge. Okay, so that would be your ionic formula there. Just remember that if you are ever making a salt from a carboxylic acid, you just take the hydrogen off the carboxyl group and replace it with the ion, the metal ion in the base. So then a solution of the impure sample was prepared. The concentration of ethanoic acid was found to be 0.45 moles per litre. Calculate the mass in grams of ethanoic acid and 200 centimetres cubed of this solution. So this calculation is not completely obvious as to what type of calculation it is. So the best thing to do with these sometimes is just write down the variables you've got. So we get given a GFM, so 60. Then you also get given a concentration. Remember I said everything with moles per litre after it as a concentration. So C equals 0.45. We also are asked to calculate the mass. So we'll put M question mark. And then we're given a volume as well. And we only need to change our volumes to litres. So that would be 0.2 litres. So that shows us we probably need to use both triangles because we're trying to work out a mass, and to do that from the GFM we need to know N, and because we know C and V we can work out N. So N is equal to C times V, first of all. So 0.45 times by 0.2, and that gives us 0.09, so that would be 0.09 moles of that. And then M is N times GFM. So 0.09 times 60. So 5.4 grams. These questions come up more in National 5 level, to be honest, so we've been a bit nice here. However, sometimes it's not nice getting a National 5 type question in a higher exam because you're almost not expecting it. So then question 5, a label from a packet of instant latte coffee drink is shown below. Explain fully why sucrose is water soluble. So you should be able to see here that sucrose has got quite a few hydroxyl groups, and the hydroxyl groups will make the molecule polar. So due to the presence of hydroxyl groups, sucrose is a polar molecule. Water is also polar and like dissolves like. So because sucrose is polar, it will dissolve in polar water. So that's the sort of explanation you want to give here. So the first mark you usually get for explaining why the molecule is polar. So sucrose is polar due to the presence of the hydroxyl groups. Try not to say that the hydroxyl groups are polar because we want to talk about the molecule as a whole. So why is your molecule polar? And then why does that mean it can dissolve in the solvent they've mentioned? So you can say like dissolves like, just don't say it on its own. I know some people think that because it says in the marking schemes like dissolves like on its own is not sufficient, that it means you can't say it. You can definitely say it, just make sure you back it up with explanations. So state what polarity your solvent is. So in this case the water is polar, restate what your molecule is. The sucrose is also polar, and like dissolves like, so sucrose will dissolve in water. Okay. So then question 5b1, there's been a question like this in past papers before, where you've got to try and piece the whole peptide back together from the tripeptides in this case that you've ended up when you've partially hydrolyzed it. So it's kind of like a bit of a jigsaw puzzle. You want to try and piece together the bits that are similar. So if we look for similar bits, we've got glycine and propene together, and they're together here. And then if we look for other bits that kind of match, we've got pro and phi. Yeah, so you've got the isopro, the glypro, and then there's the glypro bit here, which means the phi must come after that. And then we've got the phi here, which means we must then have a pro and a TYR after as well. We can't just flip them round because they're amino acids. They don't really work like that. If an amino acid is on the left hand side of another amino acid in a tripeptide, it has to stay on that side. So it would have to stay in the order of phi pro TYR. It couldn't be like TYR phi pro. It can't be switched around like that if that's a section in the hydrolysis. So it's quite a tricky one, that. So try and find the blocks that match, and then they have to stay next to each other, and then other bits can just kind of get stacked on top. So then state the term used to describe amino acids that the body cannot make. That would be essential amino acids. I think basically everyone on the planet knows that. And palm oil used in the latte cough drink is an edible oil. State the class of compounds to which edible oils belong. So they are esters or triglycerides, you can call them. Either of those is usually fine. And then when palm oil is hydrolyzed, mixtures of fatty acids and another compound are produced. Name the other compound produced. So anytime you hydrolyze a fat or an oil, you will always make glycerol. Okay, so glycerol is the molecule that's always made when you hydrolyze a fat or an oil. The table gives information on the fatty acids obtained on hydrolysis of palm oil. Name the saturated fatty acid obtained on hydrolysis of palm oil. So to find the saturated one, we need to look at their formulas. And if it's saturated, the hydrocarbon section needs to fit CnH2n plus 1. So if we have a look, 15 times 2 plus 1 gives you 31, so that's probably the saturated one. But if we just check the others, 17 times 2 is 34, so that one has actually got one less, two less than it needs, so that's going to have one double bond. And all the other ones, if we look at it, they're all unsaturated as well, because for the C17 to be saturated, it would need 35 hydrogens. So our saturated fatty acid is the palmitic acid. So then the latte coffee drink packet states it contains no hydrogenated oil. Hydrogenation takes place when unsaturated edible oils react with hydrogen. State another name for this type of reaction. So it's technically an addition reaction. Hydrogenation is a specific type of addition reaction. If you said hardening, I'm not sure that would be accepted, because that's more the name of the process rather than the reaction itself. So it's technically an addition reaction. So that's probably what they'd be looking for there. Coffee contains many different compounds. State the systematic name for acetaldehyde. So all aldehydes names end in al. This one specifically got 2 carbons, which means it would be ethanal. Just put the ending closer there. Okay, so that's how you'd want to go about that. There's no branches or anything. Then the functional group circled. This functional group, hopefully you know, is a carbonyl group. It does make this molecule ketone because the carbonyl's in between two carbons. It's not the end of a carbon chain. But all you're really looking for here is for you to call that a carbonyl. And then you've got a terpenoid. The terpenoids are classed by the number of isoprene units. Caffeine, which you're given the formula here, is a terpenoid found in coffee. Name the class of terpenoids to which caffeine belongs. So remember, when you're trying to work out how many isoprene units are in a terpenoid, or a terpene, always divide the number of carbons by 5, because there's 5 carbons in an isoprene unit. So if you take 20 and divide it by 5, that gives you 4. So then that means that you must have a diterpenoid. Okay, because you've got 4 isoprene units making it up. So always take the number of carbons, divide by 5, and that gives you the number of isoprene units. So then circling an isoprene unit. So the best thing to do for this is to find a CH3 group and then treat that as the branch. So if I pick this one and make it the branch, then this makes this carbon 2, which means I end up with a chain of 1, 2, 3, 4. So that would be my isoprene unit here. Okay. If you you're best to avoid other functional groups within the isoprene unit. So if you do see parts of the molecule with hydroxyls or other oxygens or things, try and avoid that section of the molecule if you can. So then another numeracy question. Calculate the maximum number of cups of latte coffee drink a 66 kilogram adults could safely drink without exceeding this recommendation. So we're told that 1 cup gives you 125.0 milligrams of caffeine. Then I've spelled caffeine wrong. I before E except after C, except in caffeine as well apparently. Consuming up to 5.7 milligrams of caffeine per kilogram is recommended to be safe. So we've got 5.7 milligrams per kilogram is okay. And you're trying to work out how many cups of coffee or latte a 66 kilogram adult could safely drink. So that means we can work out how many milligrams that person can drink. So we would do 5.7 times 66, and that's 376.2 milligrams. So then we've got milligrams of caffeine over here, so we can swap it over. So if we scale to 1 milligram, that would be 1 cup over 125, and then we multiply up to the amount we need. So that would be 1 over 125 times 376.2. And I've put grams here rather than milligrams, that's my bad. So if we work that out, that then gives you 3.0096, so essentially 3 cups of the coffee they could have. We'll make question 6 the last question in this video, I think. So the reaction between iodide ions and hydrogen peroxide in the presence of thiosulfate ions with starch as the indicator can be used to determine the relationship between concentration and rate. Write the ion-electron equation for the reduction reaction taking place. So for something to be reduced, it either needs to lose oxygen or gain hydrogen, or it could be gaining or losing electrons. So sometimes it's easier to find the halogen and see what's happening to it. So the halogen is going from negative to neutral, which means that's losing electrons, so that's been oxidized. So that means that then the other species in the reaction must be the one getting reduced. So we've got H2O2 going to, and that becomes just water. So all we need to do now is to balance the equation following the 4 steps. So we've got adding water to balance the oxygen, so the oxygens are balanced now that we've got the water. Adding hydrogen ions to balance the hydrogen, so we need to add the 2 hydrogen ions back in. You can kind of see them in the equation anyway, it makes it a bit easier, so that gives us 2 and 2, which adds up to the 4. And then the last thing we need to do is add in the electrons to balance the charge. So on this side at the moment it's 2 plus overall, on this side it's neutral, so that shows us we need to add in 2 electrons. Remember, the electrons are negative, so if we were to put them on that side, that would bring this side up to 2 minus, which wouldn't match. So we want to put them onto this side to bring this side up to 0 to match the other side. So if I just give myself a bit more room here, I know you can't really move your words about in the exam, but so that would be our equation there. Okay, and then always just double check the charges balance at the end. So then combining the 2 ion-electron equations to give the overall redox reaction. So again, this is a bit National 5e. You need to make sure your electrons are the same so they cancel out, which they are in this case. So this makes it very straightforward. All you really have to do is merge the 2 equations together. So you have 2 S2O3 2 minus plus the I2AQ. And if you struggle to see what's on what side, I would recommend doing squiggly lines through the arrows so you can see which side of the equation each thing comes on. It just helps your brain a little bit. Oops, and that's 2I minus. You don't need to put state symbols. You can see I've decided to put one of them. They would get ignored anyway. So yeah, don't worry about the state symbols. So then for C, you're asked, part 1, you're asked to complete the table to show how much water you need in experiment 3. So the key for these is that the total volume should be the same. So that means that they would need 10 centimetres cubed of water there, because as you can see it's kind of going up in 5 every time, but the total volume would need to be 25. And then a dry beaker must be used for each experiment. Suggests why the beaker should be dry. So like I'd said before earlier about the rinsing burettes and things with water, residue, water residue can cause dilution of concentrations, which we definitely don't want in experiments because we want our concentrations to always be accurate. So the beaker needs to be dry so that the concentration of the solutions isn't diluted, essentially, is what they'd be looking for there. And then use the information from the graph to see what happens to the rate of reaction when the concentration of iodide is doubled. So if we look at what the iodide is doubled, so the rate goes from 0.025 up to 0.05, sorry. So that means when you double the concentration, the rate is also doubled. So all you need to say here really it is doubled, or it doubles. Just saying it's increased is probably not going to be enough here. I think that would be basically a free mark. So yeah, just try and make sure you're as descriptive as possible in these things. So then use the information from the graph to calculate the reaction time in seconds when the concentration of the iodide ions was 0.025. So 0.025 concentration is here. So the rate was 0.062, because it's going up in 5 boxes to go up 0.1. So we would just do 1 over 0.062. So 1 divided by 0.062, and that gives you 16.13 seconds, or you could just say 16.1 or just 16. Just remember, it's never just going to be a case of reading the rate off the graph. You're always going to have to do 1 divided by the rate and higher. And then part 3, explain fully why increasing the concentration causes an increase in reaction rate. So if you're increasing the concentration, it means you've got a higher number of particles available for collisions. Therefore, you're going to have an increased number of successful collisions. So the rate's going to increase. The 2 marks here are coming really probably from you explaining that an increase in concentration means that you have more reacting particles. Then the second mark is most likely from the mention of what's that then doing to the number of successful collisions that are occurring. So try, when you're answering questions on factors affecting the rate of a reaction, always link it back to then how many successful collisions is that causing. Not just generally the number of collisions, the actual successful ones. Okay. And we will leave it there for this one. So if you are looking for help with question 7 onwards, then you can have a look on my Higher Chemistry playlist, like I said before, to find the videos going through that. And like I said, also at the start, the multiple choice is in a separate video too. So I hope you found that helpful. If you did, please give this video a like. Don't forget to subscribe, and I will see you again soon.